Alright, good morning. Oh, we're not doing Cuphead. Hang on. I did not prepare for this almost at all, so pardon me being dumb. Science, there we go. Did I spell that right? Did I do the word correctly? Science. Yeah, that's fine. What's up? What's up? How's it going? The title is not like some sort of vague lie. I think we're just gonna do science stuff today. Um, I would have streamed like a video game or something, but I honestly am super busy and I need to get this work done. So here we are. Um, if you haven't heard me talk about it before, I have been writing a book for a while, and I've kind of hit the point in this book. It's science fiction, horror kind of kind of genre. So I needed to learn a little bit about how space travel will work in the far future to be able to pull some things off with the book. And what I've learned a lot of things. I've learned a few things that are really, really important. The first thing I've learned is that making an intergalactic, or not, making a galactic government, like an overarching kind of federal galactic government, basically just impossible. I mean, you'd never ever be able to pull it off. Um, or it would be so difficult that it wouldn't make any sense. It would be hard to be anything other than just really kind of bad. Bad. It's like for the same reason that a global government would not function. Uh, a galactic government couldn't function, more than 10 times as poorly. And that comes down to time into space. So just the way that time works at those distances doesn't make it super simple to effectively run a government. Let me pull up a doc here. Okay, here. Put this on screen. Does Google Docs have a dark mode? View. Uh, mode? No. No, I'd like to have a visual on screen so that I'm not just speaking. Very good in podcast mode, but I have not planned anything of what I'm going to say, so I'm really bad in podcast mode. Shit. Window capture, I guess, is fine. Window capture. What is this? Browser? Browser. Oh, Google. Things I've learned. There we go. All right. I hope y'all can see this. Capture method automatic. That's fine. Oh, yeah, it's good. Oh, it's all you can see. Good job, me. Still getting things set up here, so. Bup, 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 bup. Filters. Can I crop stuff? Crop. Now, if I drag this, oh, it's just gonna make it smaller. What is the shortcut for crop? Uh-oh. Is it control? No, that's perfect scaling. Is it C? No. Well, I don't know. I'll just try and cut the top off of it. Top. What is that? Oh, buzzing. So my house has been, or my apartment has been infested with stink bugs for a while, and it's been bad. I got like 10 of them today. All right, that should be fine. Be A-okay. Good enough for government work. Of which I'm not actually doing. And then I can... Yeah, sure, that's fine. Okay, things I've learned. 1. That is not at all big enough. Okay, pardon me. Why is the crop just so bad? This tool does not work effectively. The 1,000 crop look like? No, that's too much. 200, 300. 300's fine. You'll live with that. Okay. Oh, I can also bump up the size of this. There we go. All right. First thing I learned, space government. Or pardon my spelling as well. Space government does not work. It's just bad. Bad government. Impossible. So, to make the world function, I just need to ignore the first thing I learned entirely. There needs to be space government because that's how stories are written. You don't... There's no conflict if the conflict isn't against something bigger than you, so... This is how it has to be. No one reads a story about, like... Nothing's going wrong. Just kind of in space. It's weird. So... Although I guess Interstellar was just, they were just fighting the fact that space was weird. But I don't want to do that. Alright, second thing I've learned. I don't know how to spell his name. Albert Einstein? Is that how you spell Albert Einstein's name? Is a genius. Was a genius. He still is a genius. Albert Einstein understood things about the universe that are both complicated and entirely unuseful for 99% of life on Earth, just kind of on vibes. I don't know how this guy did it. It does not make much sense at all. Like, truly genius came out of this man, and it's incredible that anyone was ever born with the ability to comprehend things about the universe the way that he did. It's fascinating. It really is. Okay. Number 3 thing I've learned. What is number 3 thing? Uh, oh yeah. When you get deep enough into relativity stuff, things just kind of work the way they work, and trying to understand that deeper doesn't really lead you down successful paths. Unless you're like some sort of physics researcher and that's the whole point of your existence. There isn't like a really impressive reason for a lot of this. It's kind of hand waved away of like, the universe just doesn't want you to do that or think about that, so just don't think about it too hard because you can't understand it. And it's not like you're too stupid to understand it. It's like understanding isn't a thing that's applicable to what it is, so don't. Which is frustrating, but just kind of the way it works. For example, in relativity, which I'm talking about both special and general relativity at the same time, because they're kind of linked, they're kind of intertwined. And the line is so small that I don't care to separate them. Anyway, in relativity, The faster you move through space, the slower you move through time. So if you're going really fast, you kind of move a little, you age a little slower, apparent to what you'd expect. Um, Technically, you age the same amount that you would expect once you start moving that fast. But if you guessed at how much you'd age before you started moving, you'd be wrong by the time you got there. In a way of thinking, it's more complicated than that. Which is part of what my issue is with this book. So, which I also need to pull up on the side. Pardon me. Oh, that closes it. Nice. I need to pull up notes for the book. Scrivener open. I will not be showing you any of my notes for this book, other than a few things. Because some stuff is just going to be hidden for now. Y'all don't need to know everything. Oh, chat's down there now. That's good. Characters. Alright. Let's go back to this. Actually, let's jump to flowchart I've had waiting. And we'll see how things end up on OBS. So, there are 3 systems that I need to worry about for this book. These will be suns. Oh, that was bad of me. Just zoom in. So, there's going to be 3 suns, 3 different systems. One of them is going to be Sun A. One of them will be Sun B. And the other one will be C. Different characters come from these different planets. There are 5 characters I'm concerned about today. And this is where things get complicated. You're kind of just sitting in on work that I'm doing anyway. And I don't know where these are actually spatially located because that doesn't make sense. I wouldn't be able to calculate that. There's also not real-life analogs for these two, A and B. There is for C. I know what system C actually is. Which makes the math a little bit easier. So, System A has 2 planets that I care about. Actually, let's make these just a little bit bigger. Or we're going to make some of them bigger. C, if C is 1, A is... Or no, if A is 1, C is 1/2. It's actually 1 over 2.3. Which is a different fraction, but decimals are fine. I'll live. I actually probably won't live. How do I remedy that? How do I remedy that? I don't know how big that is. Get a calculator that's decent. Decimus, thank you. 1 divided by 2.3. Cool, make it a fraction. 10 over 23. Which is useful for later. Also, I need a notepad. Down. Which will be... Oh, I should turn on music, shouldn't I? Very good streamer, aren't I? Chill. This can go in my work notes pile. I'm very scattered. I've got piles of things everywhere, all over my office for different projects. And it's not great. Okay, so if A is 1 over 1, I just wrote 1 over 2 like an idiot on a fresh sheet of notes. First line, bad. Get rid of that. A, 1 over 1 in mass. So that's when I say how big their sun is, or how big the system is, I'm referring to the mass of the sun. Or MOS. I hope that doesn't mean anything else. I hope not. Okay. A. Oh, let's do a table. That'll make things better. Insert table. 3 systems, probably some data points in each. A, B, C. And I will write down on my personal notes what all of these actually mean. Okay. A, the system that I'm not allowed to share the name of yet. Because it's spoilers. I don't even know how I spelled that one. Places. And then C is this other system that I also can't share. A is the planet that most people come from, so I'll set it to 1 out of 1. Makes life a lot easier on me for calculations. And this is also the capital system. B is 6.5 times bigger than A. So 13 over 2. And then C is 10 over 23. Why did I make it difficult on myself? This is just how math works out, friends, unfortunately. In the real world, things are a little bit messy, even though these are fictional planets that I made up. The reason I made them kind of strange sizes is because it gives me a little bit more wiggle room and error for being off, because it's unclear exactly when things are happening time-wise. And little differences make a big difference with the amount of time that things are taking. So if I'm like 10 years off on a calculation, I won't have to worry about people being upset when the book comes out that like, oh, this one little detail is 10 years off, because there's going to be enough slop in the system and you won't have enough information to make accurate calculations at this point, which is fine. If I eventually write 3 books in this universe and there's enough data that you could calculate it and people go, hey, you were off by 10 years when you first started this, I don't care. I don't give a shit in the slightest. Let me actually read this out. System A, B, and C. Okay. There's planets under each of these. And I'm unclear how the planets affect things. So while yes, I did learn a little bit of relativity, I don't quite get 100% how it works. It's it's very, very complicated. And I'm going to explain more into the details of how things are supposed to work as we go on. This is right now just laying out my thoughts. Okay, this has 2 planets. These are not to scale, obviously. Which is going to be A1. A2. Let me put these in spots that make sense. At sizes that are more appropriate. And these systems all have more planets than I'm depicting here. I don't care to write them all. These are the ones that matter for this try. 2 planets in this system that I care about for this book, and then system B has 1 planet, and I don't care about the rest. Okay. Oh, it all just saves my work. Thank you. Alright, let me... This is very complicated. Do I have an actual physical calculator that I can do quick calculations on? Please hold, I'll be right back. No, I gave my graphing calculator to someone I was tutoring, so, no. And I think my other calculator's in my car. I don't want to go get it. I will just work out the math on my own. I don't know the sizes of any of these planets, and I don't think they're big enough to matter, honestly. Let me over here. Figure something out. I want to see if these planets, if you could have a planet big enough to matter. Time passes more slowly with higher gravitational fields because you're accelerating. Yes, give me an equation. Uh-oh. Uh-oh, this calculation's a little bit different than the one you use to calculate how much your time dilates when you're moving at speed. It's been a while since I've done calculus, so... Okay, I need to know how far away the planets are from the star. What is G? GH is dependence of G-force on height. Where do I calculate the mass of the star? Schwarzschild metric? Non-rotating mass is spherical. Rotating objects do something to time dilation that I don't understand. That's not good. The mass of the object is m. Okay, this is non-linear, which is good. The radius you're at. So the further away you are from a giant thing, the less your time dilates, and that is proportional. Okay, so if planet A1 is way out here, very little time dilation from the star. The closer you get to the star, the faster your time moves. So if you were here, you'd be on fire. But if you were here, your time might dilate a little bit different. Cool. That's good to know. Kind of what I expected. Why would that be? Is that just because gravity's pulling on you less? No. No, it's because gravity's weaker the further you get. I think. Oh. Oh, nope. Nope, I figured it out. This one is pretty easy to figure out, honestly. It's because the further you are from a thing, the less gravity is pulling on you. So like if I dropped a bouncy ball from like 100 feet in the air, it would be slightly different gravity than something dropped from ground level. You wouldn't be able to notice because it's not a big enough distance, but okay. So do I not need to do the calculus for this then? I'd really like this to be a calculus-free night, honestly. I worked all day. Escape velocity. That makes sense. Alright. Maybe I will explain in generalities then while I learn how to do the math for this. Because it's not as simple as I thought it'd be. There's a lot going on here. It's very, very complex. So essentially, there are a few things at work. And this is to calculate birthdays, by the way. I don't know if I mentioned that. I'm trying to calculate how old all these characters are. So in this universe, your age isn't determined by how long it's been since you were born. Because again, a federalized galactic government can't do that. The record keeping would be impossible. It wouldn't be impossible, it would just be complicated to a degree that you couldn't pay enough money for it to be reasonable for a federal government to calculate that. Unless you had some sort of supercomputer, which in this universe they do not. Or nothing. They just can't do it. I don't care to explain. Completely. We're not doing the whole politics of this. Also, you'll notice the people here tend to live a lot longer than you'd expect. And their birthdays are only calculated based on experienced years. So, it is very possible in this universe that you would end up being like way older than your parents. For whatever reason, if they stayed at like super low gravity for a long time, and you stayed in really high gravity, or you moved really far away and came back. It also depends, like if you're in a cryosleep, that's not counting towards your experienced age because you aren't experiencing anything. You're just kind of in stasis for a long time. So character 1 here, I won't say who it is because spoilers, is 411 years old on star A. So relative to star A, he's 411. Let me track this as well. Character ages. Table, I've got 5 characters. This actually needs to be expanded lower. Insert row block. Character A, no, I don't want to spoil. Character A is 411. In System A, on star, or on planet 2. Character B is... I'll use lowercase for the characters, so we don't get confused. Character B is 246 in System B, so B1. Roblo. Character C is 398 on planet A.2. Character D, we'll save for a second because that's a bit more complicated. Character E is 435 on A2. So A, B, and E are A, C, and E are all from the same planet. But that's all where they base their age on. Oh, an important thing to note. Since a faster than light travel isn't anything more than just kind of a far out there theory. So you could do wormholes or something, but like we don't have a way to harness a wormhole to go anywhere faster, and we don't have. But there's no way currently to warp space so that you're not moving in space, you're just moving faster through, or no, so that you move faster through space than light could normally. Anyway, there's just no FTL, no faster than light travel in this universe. There is, which is wormholes, but those aren't harnessable to our current understanding, so no, I don't want to think about the engineering that would go into capturing a wormhole. You've noticed the characters are very old, so they've already got high enough engineering that like they're doing interesting stuff. We don't need to make it more interesting by FTL. I'd rather just not hand wave it away and go for at least a little bit of realism. Plus, this is fun. And something I've been interested in since I was like a really little kid. Well, really little kid is in middle school. Okay. Character D was born on A1, but works on A2, so they like live on A1 and then they travel to A2 for work. Not every day, but like they'll go there for a few months. They're a contractor. Yeah, they're a contractor. That's what I'll say. That's fine. That works. How would they count their age? Probably relative to where they live to what they call home, which would be A1. So that makes sense. Okay. Now, they go from, it's a bit complicated. Everyone but person B are on this planet, or on A2, when the decision is made that they need to go to System C. That's all I'll say. Oh, look, a bot. Oh, look, goodbye. Alright, I've nuked the bot. The storage is gone. We've saved the universe. Oh, can I do a different theme? Themes. Can I change the background color? I like the gray. Except for the parts that I hate. Monochrome Earth? Oh, that's cool. Can I change the background color? Because that's stark white and annoying. Alright, hang on. Can't see my Google for a little bit. I'll fix it. Images. Upload. This is gonna be really annoying, isn't it? Pictures. Isn't pictures or download? Where does Space Engine store their photos at? Is it in docs? Hmm. It's in Windows. Users. E. Nah, I can't find it. Not in pictures? I guess I could just put the thumbnail on. We should totally play around in Space Engine, by the way. Oh, that'd be fun. I like that. That game is cool. Where did I put that? Here somewhere. Hmm. Not in this set of pictures. No, I've got the Eagles logo, which I've spelled very wrong for some reason. But I don't have the thumbnail photo I just used. Alright. There we go. This is fine. This is okay. Send it back. This is unreadable. Why did I do this? Here, look at Google. Why did I do this? I'm a fucking idiot. Maybe if I outline it in white, it'll be better. I also don't know why A, B, and C are different colors. That doesn't make any sense. Outline. White. Is that more legible? I guess it's sort of better. It's fine. You'll live. Clearly, I'm not a professor of whatever science this is. Why are these two just different colors? This is so strange. Okay, they at least need to match. White, and the text color is black. Black. Okay. So, on system A, 4 characters, everyone but B. Something went wrong. Check my internet. Are we down? What's this? No, we're fine. Look, save. Yeah, we're saving it. Good job. What does this want from me? What templates? What are we doing? Alright, this is a great ad for Lucidchart. And this is not even an ad. I'm not sponsored by them. And I don't hope to be. I want this I want this toast to go away, please. Thank you. Well, I guess we'll wait it out. It'll have to disappear at some point. Okay. So for the characters, A, C, D, and E from system A go to C. They start there. Now, person B is a little bit different because they start on B1. They start in a different system, which greatly changes how your time dilation works. And also, this is not accurate. B is way bigger than A. I'm selecting the image on the outside. Great. Anyway, fantastic ad for Lucidchart. B is actually a little bit bigger than A. It's not a little bit. It's 6.5 times as big. Which means that this person will be aging much, much more slowly. I might actually need to adjust her age just a little bit, because she's meant to be younger than everyone. By a fair bit. Although I guess it doesn't matter. So person B goes to A2. Make this line curvy. Oh, there we go. Can I make the line color different? There we go. This is perfect. In a different font size. Oh, it's fine. No, it ain't. 24. A. Person A goes from B1 to A2. And then they go, all of them, go to System C. They go specifically to C1. So, on this side, it'll be C. And I actually think that's how the planets are laid out correctly. Although, I guess at some point in their orbit, they could be like that. And then everyone goes from A2 to C. I need to do the same modifications. This line, this, white, go. There we go. So now I need to figure out how old person A is in A2 reference frame. Which is going to be complicated. And I think will require calculus, which I'm not going to do on stream because I will mess it up and I'll be embarrassed. No. That's fine. And I also don't know how long this journey is, so I need to decide on that. How long are things gonna be in this universe? Far away. Okay. Oh my god. I have it set up before 24. All going to C1. I'll be able to get a lot less of this done tonight than I thought I would. I kind of thought I'd be done with this tonight. Which is fine. It doesn't impact my rating a whole lot. Just a little bit. So I don't know how long the stretch of the journey is. I do know how long it is here. Which is... oh, I don't know how... Okay, I do know how long it is in... That's fine. That's fine. This is very, very complicated. The math for this, for doing this, like, in the future when we can travel to different places, it is... Oh. Okay. I said 40, but 40 is a round number, and those don't exist in real life. Like 41.3 light years on planet A. So this is relative to planet A. That's how long this takes you. Which is weird. So let's actually talk about how relativity works, because I've not done that so far, have I? So let's say you're on System A. Pretend that System A is like Earth or something, or Sol, which is our system. We rotate around the sun. We're on Earth. There's other planets. Our system is called Sol. If this system here, C, is 41.3 light years away relative to us, that means that we here on Earth, looking at a beam of light, coming from star C would think that beam of light took 41.3 years to get here. With the caveat of not exactly, because we live in an atmosphere and light moves a little bit slower through our atmosphere than it does through space. With also the caveat that we are next to a big glowy hot ball of hydrogen and helium and all that mess that does technically change the way that light moves just a little bit. With also the caveat that to get the precision we'd need to like really understand that, it's kind of difficult. I think that's all the caveats. With also the caveat that this is the way we think it works right now, and that could change at some point in the future. Because our understanding of science could shift quite a bit. This toast is killing me. Pause. Let's pause for a second. Oh, Lucid's reloading. Oh, there we go. It's gone. Okay. So we here on Earth would think that a beam of light took 41.3 years to go from star C to us at Sol. Although that's not what the systems are in the book, so relax. No more caveats. That's just the way it works. Now, C is in a much lower gravity than we are, by half. If you went to C and you looked at light coming from A, even though all you're doing is moving from one place to another, you'd see the light hitting your eyes on planet C1 in a slightly different frame of reference, in where you'd call that light, you'd think that the light took longer to get to you. So 41.3 light years in reference from A is not the same as 41.3 light years in reference frame C. Now it's a bit complicated because things are moving relative to one another. Obviously we all go around the big black hole at the center of the Milky Way, the center of the galaxy. But you can travel the same distance, and when you get to a place, it would appear to be longer or shorter than when you first left. That's just a byproduct of the way that things appear to you when you move. There's not really anything you can do about that. One I saw recently, and the thing that kind of got me started on, not on writing the book, I've been doing that for a few months, but the thing that got me started on wanting to work this stuff out is I saw a short that was very, very misleading, that didn't make sense to me. And I ended up being actually a little bit correct with the way that with my skepticism. The clip was, of course, Mr. Neil deGrasse Tyson talking to someone else. And they were discussing a paradox called the Andromeda paradox, where, let's say you were sitting on a bench looking up at the galaxy Andromeda. Apparently there's both a bench and you in a place with low enough light that you can see that galaxy. It's actually visible, you can see it, it's like a smudge in the sky, if it's dark enough. Most places where you would be right now, you can't. Unless you happen to be, like, in the middle of actual... For example, I live in a rural area in the Midwest. I can't see it. So, there's just too much light pollution. One day I'll go to, like, Alaska or something and actually get to see all that stuff. It's on my bucket list. So you'd be sitting on a bench looking up at the galaxy Andromeda, and I, as I like to do at night, walk past people. That was a joke. I walk past you, we'd both look at the light from Andromeda and we'd see, according to the video, things happening days apart from one another. And that is true. When you move, it's sort of true. It's framed in a way that's really misleading. When you're moving, because you're moving relative to someone else, you experience things as have happened, things that are far away as having happened earlier on than the person who's not moving relative to you, or moving slower. Now that does not mean that we'd both look up and see different events happening. So like, say you got a really cool telescope and you zoomed in on a planet in Andromeda, and you zoomed in until you saw a dude on a beach playing poker, space poker. The man playing space poker, we'd both see him. We'd both see the exact same man on the exact same beach. The only difference is that because I was moving, if I did calculations on when that man existed, my calculations would tell me that he existed days before your calculations tell you that he existed. Unless I stop moving. So if I stop moving, we'd both have the same numbers suddenly. That only happens at walking speed because the galaxy is so far away and so big that you can actually see it. In day-to-day life, it's not like I'm moving so things here happen days earlier. It's far away, so the math gets fuzzy. Now that is special relativity, that's not general relativity. The way I understand it, and this could be wrong or misleading, is that special relativity happens because you're moving, and general relativity happens because some force is being applied to you. So like, general relativity is if you accelerate or if you're in gravity, that's because those are both changing amounts of force, right? You accelerate towards Earth because of gravity. You accelerate in a spaceship because you're ejecting material out the back of the spaceship. Unless you have a warp drive, which I'm not accounting for at all in this. Now, things get a little bit weird with relativity when you try to go somewhere really fast to a place that's really far away. Just generally when you go really fast. So say I was on planet A2, and I'm on the crew of people in the book that I'm writing, going to planet C1, and it, from the reference frame of planet A2, it's going to take me 41.3 light years to get there. If I'm traveling at like 99.99999% speed of light, let's pretend they figured that one out. You'd expect it to take you 41.3 light years. Or just 41.3 years, because you're moving so close to the speed of light. In reality, you, in the spaceship, could run a clock, and you'd go there, and it would have taken you like a few days. You'd just show up in a few days, and you'd be like, damn, that was supposed to take years. But we made it faster, we must have been going faster than we expected. The reality is that you weren't going faster than you expected. It's just that when you go fast, the apparent distance from an object becomes shorter to you. Now, everyone back home would have told you that it took you 41.3 years to get where you're going. And in fact, they would have aged that amount of time. So say you came back, you would have aged like a month. I think it's like 16 days or something is about this distance. Going that fast. Maybe it's a few seconds, I don't remember. I did that math a while ago. When you got back, your family would be like 80 years older than they were, so, cross your fingers that we do cool medicine, so that they're still there when you get back. And you'd be like a month older, maybe. Which is weird. And thinking about it too hard is going to give you a headache, so don't do that. The same thing happens when you're close to a star, but just a little bit different mechanism there. They're not quite the same thing going on. It doesn't appear. when you're close to something that's really big, it's kind of as if you're moving really fast because the big thing is pulling on you very hard. The same way that, like, if you're in a spaceship going the speed of light, you will have to have been pressed against the back of the spaceship, sort of, with the same amount of energy it would take you to like, be at that speed. That's kind of a weird way to say it. Now, there's kind of a method. There's kind of a method, or like some sort of thing happening in the background that I don't get fully, where you kind of trade space and time to some extent, and it's not like 1-to-1 or anything. So it's not like I move twice as fast, so I move twice as slow through time. It's not linear. It's, you know, it's exponential. So the faster you move through space, the slower you move in time, which means the faster you're going, the slower you age. So if I move at the speed of light, I age at 0. And that's where you get the speed of light at. The speed of light is just how fast you have to move to age no age at all. But so you can think of it like a photon, a little light doodad. I say doodad because it's kind of depends on what it actually is, depending how you look at it. Let's say you're a little light doodad on A2, and you want to go to C1 at the speed of light. Now, little light doodads called photons, they're not big the same way that we are. They don't have, like, stuff. It's not that they're not heavy, it's just that, well, they aren't heavy. It's just that they aren't made of the same stuff that you and I are. So they can actually go the maximum speed. The speed at which they age 0 to get to a place. So for them, they leave and they arrive. They leave A2 and they arrive on C1 in the exact same moment. So the moment they decide, I'm gonna go there, they're there. They don't have to, like, think about it. They don't have to travel. They don't have to get snacks on the road trip. They blink and they're there. Of course, it's a little, I'm generalizing a little bit. Sorry, I'm taking a little sip of my drink. Of course, we would have seen it, that little speck of light, that little beam, if you will, take 41.3 years. But, you know, if it could speak, if it could tell you everything you wanted to hear, it would come back and it'd say, no, I just went there, and I came back, and it all happened immediately. Which is interesting. To the photon would think it's teleporting. It just kind of looks at a place and then it exists in that spot. Though it doesn't have eyes, so it can't see and it can't look, or think or relay its experiences. That was just a fact. That just a little fun fact. That wasn't even part of the story I'm writing. I mean, all of this is part of it, but a little bit about light is not. That's all I can really do on the book side of things today, unfortunately. Was just work out, like, basic premises. Kind of annoying from my perspective. So, you know, in the story, this is actually to make a little bit of story sense, because, you know, if you've got friends on planet A2 and you had lunch plans for like a week from now, and then you gotta go to C1 to do some work, you'd come back and your friends would be like 80 years older than you now, which is not super cool. But maybe they wouldn't, depending on what they were doing. That's kind of why the whole federal galactic government doesn't work. Because if you're like an ambassador to planet B1 on A2 or whatever, or not an ambassador. If you're the governor of B1 on A2, and for example, this is actually what it's going to be. This was like 80 light years or something in B's reference frame. You'd go to A2 for your business meeting, and you'd come back, and everything about the place you were governing is going to be different. Life moves so quickly, and it moves quicker now every day, that once you get to the future, like, the amount of stuff that's going to happen in a year is going to be so impossibly fast that you could never, like, talk to anyone else in the entire universe without some sort of entangled system of communication. That it's things break down. Right? You'd have to appoint centuries-long temporary rulers in your place just so you could go talk to someone on a different planet. That just does not work on a human level. What I'm saying is that if we ever wanted to be a galactic government, and this is actually probably if you wanted to speculate on why humans have not found aliens yet, your answers are either all the aliens die before they can go into space, there are no aliens, which is unlikely. Actually, the first two are a little bit unlikely. The first one is more likely than the second one, that there are just no aliens. The third one is that the barrier to have aliens is much lower than the barrier to have intelligent aliens who have the resources on their home planet to actually make it off their home planet. Like, we're kind of in a special scenario where our planet's made out of stuff that lets us shoot things into space. Because, like, if your planet does not have the stuff to make rocket fuel, durable spacecraft, and intelligent life, you don't go to space. You just kind of hang out, and you get to be like water, phytobacteria, or whatever you want to be. Be whatever you want to be. Be a bacteria. Or they tried going to other planets, realized that's stupid. We can't do that. It doesn't work. Like, we go to a different planet to go, and it's 10 light years away, and we come back and everything is too different. It doesn't make sense. We'd rather just live life in one system. Those last two seem much more likely than the first two, in my opinion. I don't think people really consider this. Like, the only reason that Star Wars and Star Trek work is because they can go faster than light can. So, you can just go at ridiculous speeds, and you don't have to worry about, like, oh, my family's gonna be old when I get back, because they're not. Another way I've solved it in my book is that people don't senesce, they don't get older, so, but you don't naturally age. So if you want to live to 1,000, you can, right? But, or 2,000 or 3,000 or 1,000,000 or whatever. Did I say anything else? Is that all I have? Okay, this is a little fun fact I learned. There is an amount of mass an object can have at which there is a distance from that object past which you can't move backwards in space away from the object. So those are called black holes, by the way, if I was being a little too coy. Let's say, and it's not, let's say B is a black hole. And the actual area, or like inside part of a black hole, is kind of, you can't really know about it. You can calculate what it might be, but you can't know for certain because information can't come back from it. But let's say this boundary here, where this white area is, it has a definite surface area, but it has an indefinite capacity to some extent because the information can't come back out of it. So let's say you're a little spaceship and you get right up here, and then you go over this line. There's particulars to how that would actually look and function, but let's just say you did it. Don't think about it too hard. You go over this line. Suddenly, gravity's too high. You can't go back out within the physics of this space in black here. The space in black around B says the mass of B is high enough that you can't come back from this. That means that anything inside of B can never affect, outside of some very select scenarios that we've witnessed, cannot affect anything in the area around it. This one? That's fine. Which means that if you went into B, because it's a little bit, I guess a little bit convoluted. If you went into the space that you call B, from the outside universe, your causality, the things that you can meaningfully affect or reasonably affect in your life suddenly shrinks to everything only inside of B. So if you were to cross over from C to B, your universe in your future shrinks to this. Because you can't go back out. Which is interesting. And this is where we start kind of blurring the line between science and speculation. Is that in theory you could have different kind of parameters for the way the universe works inside of B, and because the things in B can't find their way back out into the universe, our laws of physics don't necessarily have to care about B, the inside bit here. So like if we say that this thing is massive, so if you get too close to it, you can't come back out, that's fine. B could have whatever parameters it wants on the way it exists, and as long as they never interact with each other besides the things going into B, our physics is chill with that. So functionally, B could be its separate universe. Like, you could go into space B, which has a finite surface area from the outside, and as soon as you cross over the line, you could turn around, and there could be things behind you that aren't in our universe. It's so that the inside of B doesn't necessarily have to be bounded by our space, as long as it is finite within our space, if that makes sense. It probably doesn't. It's very complicated. Yeah, black holes are cool. I don't know. We should find one and send people there. If I'm gonna die, if I have a terminal illness, shoot me into a black hole. I want to see what happens. I'd be very interested to see that. I guess it'd kill you. Probably kill you, given our laws of physics, but put me in like a suit that makes it so that doesn't happen. Put me in a special black hole suit so I can see a different universe, if that's in there. Maybe I'll just get crushed. That would be a little bit sad. As if that space outside of your causality, outside of like your world line, just kills you. Like, it would be so disappointing to have an object that could theoretically have another universe inside of it, but instead it's just like we expect it to be on the outside and it just kills you. Again, no one would know that you were dead. No one could ever know that you were dead because you can't send information back out, but except for a little bit of radiation that leaks out for reasons that I don't understand and might not there might not be reasons for it. It might just happen. Or there might be reasons that you can't know about, which is kind of the situation I had. This is bonus time. We're not talking about the book or anything that I'm writing or any relativity anymore. I'm just speculating wildly. I used to think when I was younger. That's fine. I used to think when I was younger that there had to be some good reason for everything that happened in the universe within physics. So, Stuff falls down because the sun is big, but gravity doesn't have a thing that defines it. It just is. Right? Like we can use math to describe it, but finding a cause other than mass is a thing, and knowing that like the Higgs boson is some sort of carrier for that force isn't something we've achieved. And I was always expecting like, oh, we'll find some center point, something that explains everything. And after studying for this book and trying to learn all of the relativity and things and all of the quantum physics, which is much, much less important to this story I'm telling. And of course, I've not learned all of it. The idea that you'd ever come up with something that perfectly solves all of the equations seems unrealistic. It seems like a theory to everything, if it exists, is unknowable. And that is a little bit disappointing. But I also learned that there could be universes inside of black holes, and that we could be inside a black hole. And there could be a universe that's like a layer up that could theoretically interact with us as long as it follows our rules while it's here, which is very cool. So I guess it all evens out in the wash. My sense of wonder and engagement is still there after all these years. I also finally got an answer to a question I asked in chemistry, that when I asked it, my high school chemistry teacher says, "Can you please stop asking me questions I don't know the answer to?" That question was, why don't electrons fall into the center of an atom if one is positive and one is negative? The answer to that is complicated. And it's because probably math says so, and you can't know why 100%, you just know that it happens and you can describe it. Which is also disappointing. Science is disappointing. You think you're going to learn the secrets to everything, and you kind of learn that you know how things work, but not really why so much. Anyway, that's all the time I have, because I need to go do calculus for this project now. I don't want to. Maybe I'll just procrastinate and build Legos or something. Or go drink. That would be fun too, I guess. Anyway, see ya.